Hey guys, as you might guess from the red tents behind us, we're at FMX.
In Stuttgart.
And today we just gave our talk at the side effects room here. And sorry for all of you guys who couldn't make it in. It was really crowded.
I hope that side effects will put the talk online and you can check it out on the internet. I'm pretty sure they will. For all of you who are interested in what we did, we will show the growth solver now.
But one thing that we'd like to point out is thanks so much for all the positivity we're getting back from you. The vibe was amazing. We're really just mind blown about this community. So thanks a lot. And
thank you so much.
Okay, let's dive in directly, but before we start, some theory. First, if we want to grow something, we need discrete points for the growth to happen, and that's why we scatter points inside of the volume of the object. These points are marked in blue here. And then we need a point that serves as a root for the infection, so to say. This is the pink point here in the middle. We create two groups. The blue points are in the food group and the pink point is in the infected group. And then we run over all the points of the food group and search for the infected group. Because what we want to achieve is that particles that have an infected particle nearby get infected themselves. So, using a fixed radius, we run over all the blue points and search for the proximity of an infected particle. As you can see here, this particle, this distinct particle here, does not find an infected neighbor, because the center of this pink particle is outside of the search radius. But if we look at another particle, say this one, it does find an infected neighbor. What happens next is that we loop through all the neighbors of this particle inside of the search radius and look up their value for infection. The food particles, here blue, have no infection, so the infected value is 0. But the pink particles have an infected value of 1. We then just generate the average of these values and write this value as the new infected value of our searching particle here in the middle. That means that, say, this particle has an infection value of 1 and this has one of 0, this gets an infection value of 0.5. To make this even more realistic, we can take the distance here into account. So what if we use a distance here between these two particles and these two particles? You see this distance is larger, and then we weight the infection value that we look up by the distance. That means that this particle here has a bigger influence of the new infection value of this particle than this one has. So the next step is, in the next frame, the same process happens again, and this particle gets another bunch of infection from this particle here. And now something interesting happens, because now the value of this particle, the infection value of this particle, exceeds 1. This is just an arbitrary threshold. We can pick whatever we want. I picked 1 in my setup. Now we want to make the particle switch groups, indicated by this orange outline. So now this center particle switches from the food group to the infected group. And that means that in the next step, all the blue particles will not only find this particle here, but this one in the middle too. So now if we again look at this particle here and see what happens, now it finds an infected neighbor and slowly accumulates the infection over time and eventually switches group. This search paradigm makes the infection grow outwards from the originally infected seed and eventually make all the particles infected. And this looks very natural because it somehow models what happens in real life with infections. Okay, let's dive right in and get this thing built. I already imported the model I built in 3D Code, but it can come from anywhere. It's a simple crystal sculpt, and I want to make this grow. I transformed it down because 3D Code usually has very big objects compared to the scene size of Houdini. The first thing I need is I want to scatter points inside of the volume of this object. So this is a surface object. To make the scatter node scatter inside of volumes, I first have to convert this into a volume. And I prefer using VDBs, so let's create a VDB from polygons. Call this fog, because I intend to use a fog volume for this. And tick off distance VDB and tick on fog VDB. We just keep the default name density. Now connect this, make it visible. And it will create a fog volume. It's just that you don't see it because of the bright background. So I press D, go to background and change it to dark. That's pretty much a standard workflow if you're working with volumes. You see that it's already a volume, but it's very coarse. So let's go down with the voxel size, say 0.005 might be a good value. This will take a second to calculate, and now we have a very nice representation of our object as fog. Now for scattering. The most natural thing is to scatter with the scatter node. And if you connect it to a fog volume, it will use the density for scattering. You see here we get nice volume distribution of points. If I turn off the relax iterations, you see that the scatter node is scattering random points inside of the volume. For our particular case, this is not optimal because crystals have a very regular structure to them. They are either tetrahedral or they are orthogonal, so grid-like, but they are not that random. And this, of course, influences the growth behavior of the solver. So instead of using the scatter node, there is a better node for this in Houdini called points from volume. From volume, this is from the fluid toolkit, and it's used to prepare particles for flip sims. And you see, if I activate this one, I get a very regular grid of points inside of the volume of my crystal. A little bit coarse at the moment. You can specify the resolution with this point separation value, and let's put 0.01 here, and this gives me the whole volume filled nicely with points, as you can see. So let's get rid of the scatter node, and now we prepared the food points, so the points that will eventually end up switching groups to the infected group. Now I need a group node, so just append a standard group. And if I click on this and switch it to points, I have all the points in my group and call this food, because this will be the food group, all the points. So the next thing is that I need a seed point. And I can just use an add SOP for creating a seed point. So this will be a second geometry stream. Just create a point. Let's quickly use a copy to points and a sphere, because that makes it easier to visualize where our point is sitting. And now turn on this checkbox here, which will create a point at the origin, 0, 0, 0. You can go over the viewport and hit the return key, which makes the handle tool active, and that allows you to move the points manually. And if we now show all the scattered points and maybe shrink the sphere a little bit, you can see where we are, and you can move the point around, let's say, to here. You see the values here are updating. Now we have a nice seed point in the middle of our scattered food points. What's next? Well, we want to put this point in the second group, so create another group node, and we will call this group infected. Now we have a lot of food points and one infected point in the middle. For the solver, we will need all of these points inside of one large bunch. So lay down a merge and just merge these two geometry streams together. Make sure to use the group here and not the copy to points, because this is only for visualization. And if I middle click here, I see I have 1,116,364 points, and here I have just 1 point more because this comes from this geometry stream. Now great, we have prepared everything we need for the solver, in principle. What's missing is the solver will use attributes to do its magic, and we have to somehow initialize these attributes on these points. For initializing attributes, I'd like to use the wrangle, because for me it feels most simple to use a wrangle. So just create a point wrangle and append it here before the group, and I call this initialize init vars, or even better init attributes, like so. Let me press Alt E to open the expression editor, and we want to create a value infect. So this will be a float, so F and then N infect. And on these food particles, the infect value will be 0 because these are not infected yet. Semicolon, apply and accept. Now we can just, with Alt and drag, duplicate this node, shake it off and put it here on the other geometry stream, and on this side the infect value will get a value of 1, because this particle is already infected. Now, let me reorganize the network quickly by pressing A and dragging down. I can tidy it up, like so. Great. Maybe move this out of the way, the merge in the middle. Now it's time to go into a solver. So, create a solver. This is a SOP solver. The SOP solver is basically a DOP network. So if I dive inside, you see here on top of this path chain here that this is basically a dynamics network. And inside of the dynamics network, we have a SOP solver node. This SOP solver node is a DOP that allows us to use SOPs for dynamics purposes. So this whole solver is a little bit of a Christmas parcel. It's just packaged up. So if I double click, it directly jumps inside of this SOP solver. But keep in mind that in reality, it's a DOP network. And the DOP network allows us to use attribute values from the previous frame. This is a big difference from SOPs to DOPs, or one of the big differences. Using the SOP solver here, it's really the only difference. It comes with 5 nodes, input 1 to 4, and then previous frame. These inputs here are just these 4 inputs. So whatever I connect to the 4 inputs comes out of these nodes. And then this node is very important because it gives me the geometry that I had in the previous frame. So whatever node I make visible inside of the SOP solver will come out here in the next frame. Because I want to use these values, I will append everything at this node here. But we have a problem with this because in frame 1 there is no previous frame. So in frame 1 there will be no data coming out of this previous frame node. So what we can do about this is use a switch node and switch between this node and this node. In the very first frame we want to use whatever comes out of input 1, and after that we will use what comes out of previous frame. To make this work we will use a expression here in this select input field. And this expression is just $FF for a simulated frame, so the floating frame. And whenever this is 1, it will be 1. That means this branch gets active. Whenever this is not 1, it will use this branch here. So now let's go up 1 level and connect the data into input 1 and make the solver active. Now the next thing is that we'll need another wrangle to write our solver. So put down a point wrangle. Here it is, and this will be called growth solver. Like so. And press Alt-E again to open up the expression editor. And here we will write our solver. Let's just implement what we thought about in the theory section. The very first thing we'll need is a search radius. So let's define a new variable of type float. Let it call radius. And this will be 0.05. I just tested different values and found that this is a good value for this scene size. Now that we have that, we'll need the neighboring points for every point that we are searching on. So let's do a point lookup. And for this we use a near points expression. The near points expression returns an array of all the points that are within the search radius. So to store the result, we'll need an array. The array is of type integer because it holds the indices of the points. So create a new integer variable. I call it nbrs for neighbors, and then directly after this I specify square brackets. And these square brackets tell Houdini that this is an array variable, so it will hold an array instead of a single value. And this array will be filled by the near points expression. So near points, brackets and semicolon, and then we will have to specify the geometry stream it's working on. That is just the very first input. And then we can specify the group to look in. So we only want to look inside of the infected group for target points, because we know that all the food points are not infected yet. And this will just speed up the calculation. So put infected here. Next, we have to specify the attribute we want to look up, and this is at P, because we want to search for the position. And last but not least, we have the radius we defined earlier. So this operation will give us an array of all the closest points inside of radius to the currently processed point of the food group. Now that we have this nice array, we want to run over the array and look the infected values up and sum them all up. To do so, we need two organization variables. First, we need a count, because we have to keep track about how many points we are running over. And then we need an accumulation variable. I call it accum and initialize it with 0. And now comes the loop. I want to run over all the points in the neighbors array. And to do so, it's easiest to use a for each loop. So write for each. And then we need a counting variable. In our case, this is an integer called neighbor. And it will run over the array called neighbors with an S. So what this specifies is, please go over all the elements you find in the array nbrs neighbors and store the currently processed element in the integer variable neighbor. And this has to be an integer because the array is an integer too. Now, curly brackets to define a block, like so. Everything within these brackets will be executed in the loop. So, what do we want to do inside of the loop? First, we want to look up the infection attribute on the points that we found. Let's create a new variable of type float, call it infection. And now we look up with the point expression the value of infect of the points we found. The point expression needs to know on which geometry to operate, so again 0 for the very first input, and then it needs the attribute, which is called infect, and then it needs the number of the point it should look up. And as the for each loop will store the currently active point number in NBR, we can use NBR here. Now we are gathering the infect attribute from the closest point, from the first closest point in the array. The next thing is to accumulate all of the infect attribute values from all the points in the array. That's why we defined the accum variable before the loop. So let's add to the accum variable by writing plus equals infection. What this does is it will add in every loop iteration the current infection value to the accum variable. Thus, after the loop finishes, we have an accum variable that is a sum of all the infect values of all the particles we run over. And before we finish the loop, we want to increase the count by 1, like so. Because we later on don't want just to use all the summed up values, but we want to calculate the average value, and to do that we have to know how many values we summed up. And now what we can write is, please update the attribute infect, and this is referring to the infect value of the currently processed food point with the current value of infect plus the sum that we stored in accum divided by the count. But be careful, the count is an integer, so we have to convert it to float first, otherwise the division might not work. Like so. So that means, please update the value, so store to the value the original value, and in our case this is the value from the previous frame, because it comes in over previous frame, plus what we calculated as the sum divided by the count of elements that forms a sum. And this is the average value. So now it goes through all the nearest neighbors, adds up their infect value, and puts the average of all these values on the infect attribute of the currently processed food particle. Let's apply and accept. Quickly open up the expression editor again, because I forgot a comma here before NBR. Accept again. Now we are accumulating the infection value. What's missing is to switch groups. I like to put the code to do this in a second point wrangle, just to keep it organized. Call this switch groups. And open the expression editor for this one. In here we write an if statement. If the infect attribute, that is the infect attribute of the food points, is bigger than 1, then and only then execute what is inside of the brackets, and this is group infected will be 1, and group food will be 0. These add group underscore things are shortcuts to define group membership. You can do this with a function, but it's easier to do it like this. So you can just specify group underscore and then the name of the group, and Houdini automatically binded this value here. And if you then give it a 1, it means put it in the group, and if you specify 0, it means take it from the group. So this whole statement just indicates that whenever the infect value of one of the food points is bigger than 1, it switches group from food to infected. Let's accept this and put the display flag on this switch groups node. Time to test our solver. But before we can do this, one little thing is that I forgot to switch the group type on this group 2 node to points. It won't work on primitive. And then we will need a blast node, because we only want to see the points inside of the infected group and not the points in the food group. And if I do this, you get this blob here. So now let's play the simulation and look what we got. The good news is it's working, as you can see here. But A, it has this not very round shape to it when it's growing, and B, it's not very fast. To make it faster, we can do a very simple thing. Let's dive inside the solver quickly and just say that this growth solver should only process the points in the food group. By doing so, we exclude a lot of points from the processing and thus make everything faster. And the same holds true for these switch groups. And if we now go up, everything will be a lot faster because it has less points to process. So it's only running over the food points and looking up the infected points, and this gives the speed boost. The second thing is to address this not very round growth behavior. And to change this, we will implement weighting by distance. Let's do this now. So jump into the solver again. Let's make the growth solver active and press Alt-E to open the expression editor. What we will do here is we want to add a weight variable and multiply the infection by this weight, and this weight will be calculated from the distance. That means first we'll need a distance. So let's create a distance variable. I call it dist. And this will be the length of the vector between our processed point and the nearest neighbor currently processed. So this is length, to calculate a length from a vector. And in here we want to calculate the vector itself, and that is the current position at P minus, and now we have to look up the position of the point in the loop. So another point expression, give it input number 0, and then the attribute to look up is P, capital P, and NBR for the point number. So this will calculate the distance between the point that is processed and the neighbor that is currently processed. Now we have the distance, that's good. Next we want to create a weight. This is a float again. I just call it weight. And this will be a function of this length. But where the length is small, this value should be high, and where the length is not so small anymore, the value should be lower. So I will state 1 minus to generate the reciprocal of the length, and I want to smooth the length. The smooth function is like a fit function, so it changes the value range, but it does so smoothly. It has an ease in and ease out, so to speak. So let's specify it should smooth from 0 to the maximum value of radius, and the value to smooth is distance. So that means this function will be 1 wherever the distance is equal to the radius and 0 otherwise, and we generate the reciprocal of this. And this will be used to multiply the infection with, to weight the infection by distance. So let's see what this gives us. Rewind and play, and you see now the growth is nice and spherical. Now that the growth is working nicely, what's left is to mesh the particles to give us a growing surface. We can do so with the same tools that we use in fluid meshing. That is VDB from particles, for example. Let's append a VDB from particles node here and connect it. But before we make it visible, let's go in and change the sizes, because the sizes are just way too large. Go to 0.01 for the point radius scale, and to accommodate for this scale we have to specify a voxel scale that is even lower, otherwise the time distance field would not be able to represent the points. What this node is doing is it's generating a spherical influence region around every point and then building an SDF from these influences, like you can see here. It gives us a nice surface, but it's very, very blocky. It looks very voxelized. What can we do to smooth this out? Well, we can append a VDB smooth SDF here. But the problem with this approach is if we go up with the iterations and the voxel radius, say 2 and 8, it shrinks the surface a little bit. So to counteract this, we will use a VDB reshape SDF. And this gives us operations like delayed and erode. So if we use this here and dilate our volume, let's say by 3 voxels, now we have a bigger volume than before. Now we feed this into the smooth, create a smooth surface from this, and after that use another VDB reshape to counteract what the first did by eroding by 3 voxels. And now we have a surface that is pretty much in the same place as before, but is smooth. And this is pretty much it. What's left is to shape the outer surfaces of this blob here. We can use a combine VDB operation to just subtract the original model from this one here, or intersect this one with the original model, to generate sharper outer surfaces. So if I go up here and create a VDB from polygons again, but this time we will use an SDF and go lower than this, like so. Now we have our original crystal, and here we have our growth surface. And now we can use a VDB combine and intersect both of these by doing SDF intersection. And you can see that this gives us a little bit of the original model back. You see the original model, our growth model, the original model, and our growth model. The problem is that our growth surface is just more or less at the same place where our original model was. That's why I get these cut-off areas only here in these concave areas. So another thing we could do is to make the whole growth thing a little bit bigger than the original model. And we can do this by going up our tree and just before this fork here, append a peak. The peak node will just extrude or move the point of the volume along the normals. So let's say 0.05, make it a little bit bigger, and then feed this into the fork volume. Now the fork volume is bigger, and the points from volume will be bigger. And the whole growth process will generate a bigger surface. Because we changed the input, we have to rerun the simulation. Let's do this. And now if I make the VDB combine active, you see that I get all the nice harsh edges from the original model back, because now the growth surface is a good amount larger than the original model. So by combining both, I get the original surfaces on the outer rim, so to speak, and wherever the model is growing, I get the new surfaces. So This sums up the behavior of a simple growth solver. Let's do a quick flipbook and look at the result. And here's the result. Propagation grows inside of a volume, and it's growing the crystal. There are many ways to vary this to make it more interesting. You can move the seed point around, you can scatter more than one seed point, you can introduce other weighting factors, like for example you can map a noise to the original point and use it as a weight, or you can even alter the distribution of points. The possibilities are limitless. This is a very flexible way of growing your objects. And this concludes today's lesson. I hope you learned something. I hope you found it useful, and see you soon.